Here we're just going to talk about a few miscellaneous things. I honestly never even give notes over this stuff here. I usually just refer students to a few examples in the book there, and I tell them to do some independent learning with some of this stuff. But we're going to talk about the average value formula. We're going to talk about an integral as an accumulator. It'll add stuff up for us and give us the total, like a net result. And then we're going to talk about displacement and total distance traveled right here. So we're just going to talk about a few things. I'm mainly going to refer to a few examples in the book there and talk about a couple of things real quick here. And then you kind of figure some things out on your own. And the one little section, it's just some miscellaneous stuff that I think we already know. Like if you have the integral between 1 and 4 and you add in the integral between 4 and 7, that's going to equal the integral of the whole piece in between 1 and 7. Just like if you have like a big stick and then you just like break that, you know, you're going to throw it to your dog or something like that, you know, play fetch, like that's just a little piece of the stick. That's another little piece of the stick. And you add up the two pieces, that equals the whole entire stick right there. All right. So this is, you're allowed to add and subtract the integrals like that and with the different pieces there. If you ever have the need, it doesn't happen often, but on the AP test, we will need to sometimes switch the numbers attached to the integral. If I ever have the need to switch the numbers attached to the integral, what you need to do to keep it equivalent is put a negative in front. Do the opposite sign right there. So whenever you flip the number, so the general rule is if you flip the numbers like A to B, if you flip and make it B to A, then you gotta make it the opposite sign right there. And the reason for that, because if you integrate, like if this is your f of x and you integrate that and you get your antiderivative, right? And you plug in, evaluate that from 4 to 2. So then you would do f of 2 minus f of 4. Well, on this one, when you evaluate it, you get your f of x. And then when you plug in the 2 and the 4, see now you have f of 4 minus f of 2, and see how those are going to be different unless you put that negative in front of there, and now it becomes negative f of 4 plus f of 2, and you're making them equivalent again. So if you ever have a need to switch the numbers, that's the little property right there. If you ever need to flip the numbers there, because most of the time we need it to go least to greatest. So if you ever encounter this and you're going to flip it, but then if you flip it, just switch that sign real quick. And then another little property that's pretty much common sense, I think, is like if you integrate from 4 to 4, I'm hoping you know you kind of expect to get 0 for that. All right. Technically, remember your integral is an area. So if you do the area of a point, there's nothing underneath the graph right there between the graph and the x-axis there. So it's just going to be 0 for the area. Also, if you did it algebraically and you integrated that thing, made that x cubed over 3, and you evaluate that from 4 to 4, you realize when you plug in, you're going to get 64 over 3 minus 64 over 3. And that's always going to be 0 right there. So there's another little property there. And then what we're going to talk about, so I'll get us through that one section, and we go through the other section. There's a few miscellaneous things in the book. The one more really important formula right here is your average value formula. All right. So when you do your average value formula, you'll see something like average value, right? And it's just 1 over b minus a times the integral from a to b. So your integral will add up a bunch of stuff for you there, or calculate the areas, and then you're going to divide it by the length of that integral. All right, so 1 over b minus a times the integral from a to b, that's your average value formula. So if you look at this one example here, this is on page 286, by the way, but if you look at this one example, I give you a function, say find the average value over that interval. So there's your a, there's your b. So I'm going to go 1 over 4 minus 1 times the integral from 1 to 4. So you integrate that, plug in the 4, plug in the 1, times it by the 1/3. You're going to get that 16 right there. And you know what an average value is. That's the average value. So like that's the average y value on this curve. So there's your quadratic. And then sometimes, so that's your average y value is going to be 16. Sometimes your y value is less than that. Sometimes your y value is more than that. But see, that's changing. It's not like a linear function where you can do a normal average. So that's what this does. It'll add up the stuff for us and divide it by the length of that interval. And the integral will account for the things that are changing right there. So that's what that'll give us. So on the AP test, if they talk about like, hey, they're talking about the number of cupcakes, right? And they say find the average number of cupcakes, then boom, you're going to do the average value formula. So if you see the phrase average rate of change, that's your slope formula. F of b minus f of a over b minus a, the average value formula, that's your 1 over b minus a times the integral from a to b formula right there. And then whatever the units are in your original problem, and typically is what your units will be for an average value problem there. Because like if you have like feet per second, when you integrate it, you're going to get feet, but then you're going to divide it by seconds again, and it'll be like an average velocity or something there. So it's going to remain feet per second there. But that's just a real easy formula. When you're doing average value, for these few problems, you can stop right there. You don't have to do what the back of the book does after that. Once you find your average value, that's all we need to be able to handle. And that's what we got to know on the actual AP test right there. So just use that formula, find that average value, and then you're done. And one other interesting, useful thing in this section, go over a couple pages there. It's pretty much like the net change type of stuff there. So notice that here we got a problem. Just the integral is an accumulator, okay? So when you have these word problems, they're really not difficult, but see, it tells us a chemical is flowing into a tank at this rate. So this is liters per minute. This is like they're giving us the derivative, and then they're asking us find the total amount of chemical that flows in there. So we want to go from liters per minute to liters. That's like going from a velocity to a position, all right? How fast something's going to just the total amount. So if you want that total amount, integrate that. When you integrate the liters per minute, you're going to get liters there. So that's why when I just integrate that derivative in between it says for the first 20 minutes. So you integrate that between 0 and 20. It's an easy problem. Plug it in, and we're going to get the total amount of chemical that flows into the tank for the first 20 minutes is the 4,200 liters right there. So that's what I'm talking about, the integral as an accumulator. When you see a word problem, you know, it'll do that easily for us. And then that'll help us to interpret our answers. A lot of times on the AP test, they would say, what are the units, or interpret your answer. Well, if you know the units go liters per minute, like if I'm doing a derivative of liters per minute, that gives me liters per minute squared, like a velocity to an acceleration. But if I'm going to integrate that, that per minute part will drop off, and I'm just going to get liters. So if they ask me to interpret my answer, that helps me interpret my answer like that's the total amount of chemical that flows into that tank right there. And if I have liters per minute as my units, that helps me interpret my answer as how fast that chemical is flowing into that tank. All right. So you got a couple easy word problems like that. And then probably the thing that gives us the most trouble is this whole idea of displacement and total distance traveled. Okay, so if let's say we have like a mouse in our house, right? And then you drop a little piece of cheese or something on the floor, right? And then he comes out of his house, and then you see him, and you try to swat at him with a broom or something like that, Tom and Jerry style. So then the mouse just goes a little bit crazy, right? And then eventually he just jukes you out, and then he just ends up at that piece of cheese, and then he's happy. Now, maybe you swat him after that. Maybe he gets back to his house, but at least for the time being, he's going to enjoy that piece of cheese right there. Or maybe he'll try and lug it back to his house or whatever. But see, he ran a lot of distance there. If I want to know what the total distance travel is, that's all that squiggly stuff. However, if I unwind that squiggled line and measure that, that's the total distance traveled, right? But see, if you just want the displacement just means where is the mouse from the starting point to the ending point. So this purple line here, this is your displacement, and that's just your net result. Now, if you want to find the displacement, the formula for that is you're going to do the integral of the velocity, just a normal integral. The integral will give you the net result. So if the portion of the graph goes below the x-axis, it'll know to subtract that out. If the graph goes above the x-axis, it's going to know to add that in. So if the mouse goes backwards and forwards, it doesn't matter. I just want to know what that net result is. That's your displacement. If you want the whole line all unraveled, that's your whole line. That's your total distance traveled. And then your total distance traveled, then you actually, if that mouse goes backwards, you want to count that distance still. If it goes to the left or to the right, you want to count all those distances. You don't want the net result. So since you want to count even those negative distances as positive, you want to count everything. The total distance traveled is the absolute, you integrate the absolute value of velocity. It's just like a football player. He gets that kickoff return or that punt return, and he might run to the left, he might run to the right, he might run backwards, and then he might run like 50 yards total distance traveled, but he only might have gained like 3 yards total. If he goes this way and then back this way and tries to get around people and then gets tackled right here, his displacement was 3 yards. That's your net result. But his total distance traveled, if you want to count everything, even when he ran backwards as the total yards that he ran, that's, you want to count everything, and that's the absolute value right there. Now, it's always easier to just integrate the normal velocity. When we integrate the absolute value, I'm going to show you how to do that right now. Okay, there's a perfect example in the book, and then we got a couple to try in the homework that I want you to try on your own there. Okay, so this example here, this is page 292, by the way, gives us a particle is moving along the line. It gives us the velocity function. It wants to know both things, the displacement and the total distance travel. So the displacement in between 1 and 5, that's easy. Okay, you're just going to do your integral of the velocity. You want that net result, and so it's a little glaring here. So you want the net result, right? So you integrate it normally, plug in the 5, plug in the 1, boom, there's your displacement. Very simple, okay? So we typically don't have any issues finding the displacement. It's a total distance traveled that we got to be careful on. So when you do the total distance traveled, here's what you gotta do. We need to integrate the absolute value of velocity. Now, when you integrate the absolute value of velocity, here's what I always do as I graph the velocity function, okay? Here's the graph of the velocity function. And so, and then I notice where it goes above and below the x-axis. Now at the beginning here, it's probably gonna be easy to see, oh, in the graphing calculator, oh, it's crossing the x-axis at like 4, 3, or something like that, right? When they get a little bit more involved, we'll show you how to calculate that zero. But all I do is figure out where it crosses the x-axis, where it is above the x-axis, where it is below the x-axis. And I do 2 separate integrals, or I do 3 separate integrals. If it goes above it and below it again, then I got to do more integrals there. But basically, whatever is above the x-axis, you do integral for that. Whatever is below the x-axis, you do a separate integral for that. And then, so here's the thing. So when I integrate between 1 and 4, I'm trying to do the absolute value, right? So when I integrate between 1 and 4, that velocity is already above the x-axis. It's already positive for me. So I could just do the normal integral wherever the graph is above the x-axis. So I integrate between 1 and 4. I expect a positive answer. Notice when we integrate a plug in the 4, plug in the 1, we do get a positive 45 over 4. And then here, when I integrate now the normal velocity function in between 4 and 5, when I integrate the velocity in between 4 and 5, I expect a negative answer because this graph is below the x-axis. But what I'm really trying to do is the absolute value, so I know it's supposed to be positive. So what I do is when I integrate the part that is below the x-axis, I compensate for that right at the beginning. I stick a negative right in front of it right away because I can expect a negative answer right here because the graph is below the x-axis, but you know the absolute value is really flipping it up and it really should be positive. But see, I'm not going to be able to get this 7 over 12 number unless I integrate that velocity because that's just a curvy, thing right there. We need the integral to kind of get that area. So when you have the absolute value of velocity, the total distance traveled problem, graph the function, whatever is above the x-axis, do a normal integral, get a number for that. Whatever is below the x-axis, you could either integrate it, get your negative number, and then make it positive, or you could just stick the negative in front of it right away because you're going to expect a negative answer for that, and then you stick a negative in front of there. So notice when I integrated between 4 and 5, we did get the negative answer because it was below the x-axis. And the fact that I put the minus right in front of there made that plus a positive, and I added that up right there. So just, you got to work at that. You do got a couple of problems that you can check for, but that process will always work no matter what your equation is going to be. So just work on that, try to model that the best that you can, and do the best you can with that, and then we'll do some other questions there. So I hope that just gives you a little direction. Like I said, usually I just refer to students, I tell them to read those examples in the book there, and I just tell them to figure that stuff out on their own. But hopefully that gives you a little bit more instruction than what I normally give, and then we'll do questions after that. Thank you.